Hi, good evening. Can you hear me and can you see my screen?
Yes, sir.
Okay. We'll wait for one more minute and then we'll start it from 6:10. Let's see if someone else joins.
Okay, sir.
All right, we'll start and we'll let others join. So this is the 10th doubt clearing session of the course by Professor Debapriya Das entitled Fundamentals of Electrical Engineering. I am Shatur Shide. I am a PhD scholar at IIT Bombay. I take this class every Monday, 6 to 8 p.m. So this week's topics are magnetic circuits and single phase transformer. So this is going to be the very first electrical machine that you are going to study in, in this course or in electrical engineering, assuming that you are first year students. So before I start, I generally ask for doubts if you have watched the videos of this week and if you have any doubts of this week or any other week. Okay, the one student left. Hi Deepak. I started with some introduction. Only one student was there, but she left anyway. So yeah, today's topic is magnetic circuits and transformers. Have you watched the videos and do you have any doubts anywhere?
No doubt.
I can't hear you. Could you please be louder?
No doubt, sir.
No doubt. Okay. All right. I will give a very brief introduction about magnetic circuit and coupled magnetic circuit. I've seen in the last two semesters of NPTEL classes that many students have misconception or do not have the conception of magnetic circuit and how to handle them. So I'll give one introduction about it, about coupled magnetic circuits. Before that, we will start with regular magnetic circuit. Now, if you look at electrical circuits and if you look at magnetic circuits, they are very similar. They are very similar and they can be analyzed the same way. Only thing is that you have to know the analogies. Okay. Uh, Now, in electric circuit, there are three variables, or not three variables, two variables, which are voltage, current, two variables, and several parameters, of which we will now talk about only the resistance. Okay. Now, when you are solving magnetic circuit, their analogies are the voltage becomes the MMF, magnetic circuit. Do not think, sorry, I should not say voltage becomes MMF. The analogy of voltage is MMF. Analogy of current is flux, and analogy of resistance is reluctance. Now, say if you have a magnetic circuit like this, say so it's some alignment problem. Some magnetic circuit like this, there is an air gap and one more iron piece is here, and say there is one coil which is connected here in this fashion. Right? Now you are asked to find out flux and magnetic flux intensity in the circuit. Now what we can do is the relative permeability of iron or magnetic materials, that is very high, in the range of say 4,000 to 6,000, whereas the relative permeability of air or vacuum, we know that is 1. Vacuum it is 1, air it is close to 1. So in this circuit, majority of the reluctance will be mm, provided by the air gap. So if there is no data, we can always neglect the reluctance offered by the iron path. If there is data, you can take. Now, if you draw the equivalent electrical circuit, so the way to solve any magnetic circuit is to draw the equivalent electrical circuit and then solve the circuit. So the equivalent electrical circuit becomes, so the three air gaps will be represented by three resistances. Means all the air gaps will be represented by resistances. So I can draw them like this. So this is the equivalent electrical circuit of the given magnetic circuit here. Now, what is a voltage source? Voltage source is MMF. What is MMF? MMF is number of turns times current. So if there are 10 turns and 5 ampere current is flowing, you have 50 ampere turns of MMF, right? And how to solve the same thing, like you in electric circuit you have V equals IR KVL, Ohm's law, sorry. Similarly, in magnetic circuit you have MMF equals flux times reluctance, and you can as usual apply KVL and KCL in magnetic circuit also. So it's basically in magnetic circuit the KCL will be in terms of flux. Say the flux, or if I show here, say the flux going out phi 1 in this way and in this way, that will be a summation of this. So here we can write phi is equal to phi 1 plus phi 2. So the regular KCL that works, it works in magnetic circuit. So this is the way to solve magnetic circuit. Now, yeah, I'll just make one comment or tell you the very basic of coupled magnetic circuit. Coupled magnetic circuit. Now, in a circuit, the sense of winding is depicted by means of dots. So coupled magnetic circuits are often shown like this. So one dot here, one dot here. So there is something called the dot convention. Now, if you look at the several textbooks, several websites and all, there are 100 types of definitions. You will see that all of them at the end boil down to the same thing. They, if you follow them, if they are correct, they will give you the same output. So maybe you can remember your definition. The definition that I go through is that if there is a current I entering the dot terminal, and if this current is increasing, then it will give rise to a positive polarity on the dot terminal of the other coil. So if this I entering dot terminal is increasing, that will give rise to a positive voltage or a higher potential on the dotted side of the other coil. Now, to write this mathematically, or to write this in order to solve the circuit, how much this voltage will be, if we want to know, what we can do is we have to manually decouple the circuit like this. So say I call this current I1 and call this current I2. So as much generalization is possible that we are doing. Again L1. So now what I am doing is I1 and I2. Now see, I am not drawing the coupling anymore. So the circuits now are not magnetically coupled, but who is taking care of the coupling? This dependent voltage source is there taking care of the coupling. So now if I draw this, since increasing I will create, so if I write A, B, C, D, since increasing I1 will create a positive voltage at C with respect to D, then definitely this one will be M di1 dt. M is the mutual inductance. Similarly, you can see this becomes M di2 dt. So you see the coupling is still present mathematically, but now physically we can consider the circuits to be isolated. They were anyway electrically isolated. Once we write this equation, they are physically isolated also. Means magnetically isolated also. Any doubt up to this? Okay, we will quickly go through what do we mean by dot convention. Like say you have a transformer, a physical transformer like this, where the windings are placed in this fashion. So this is one winding, say, and this is the other winding. So the winding sense is like this, right? Now when you are making a circuit, it is important to know the sense of the winding before connecting this transformer to a circuit, right? Because the terminals are not equivalent. So how to put a dot? How to put a dot? How do we know? Now the thing is, say if I draw one inductor in a circuit, I just draw one inductor in a circuit and put a dot. That doesn't make any sense. Dot with respect to what? So here to start with, we can put a dot anywhere on one winding. Now once we put a dot on one winding, there can be other multiple windings also. So we can start. So this becomes our reference. We have to put the dot based on this on the other windings. So what we take is a current I. Now we will apply our definition that we just learned, that if this current I is increasing, it will induce a positive voltage on the dot terminal of the other coil. Now see, if this is a current I, so it is flowing like this, and by right hand rule you can say that this creates a flux phi like this, which goes down in this branch, phi. Now, if this current is increasing, then this flux is also increasing. By Lenge's law, the other side of the blue coil will try to induce a voltage or a current so as to oppose this flux. So the other side will try to create a flux in this direction. So by right hand rule, you can say that the other side will try to induce a current in this direction. Then only it will create a flux like this. So in this direction, it will try to create. So basically this will be at higher potential than the other. So we can say if I put the red dot there, for the other terminal, the dot will come here. Now notice one thing, that it is relative. So you have two coils. I can put the dots here and here, and this is equivalent to putting the dots here and here. Similarly, if I have two coils like this, I can put dots here and here, which is equivalent to putting dots here and here. Okay, same thing, it doesn't matter. But once you put dot in one terminal, or sorry, in one winding, for the other windings the dots get defined. Any guess until this part? Any doubt until this part? Okay. So we'll gradually start solving. Okay, one last derivation we will quickly do. Okay, Deepak, do you know this thing that inductance is n squared permeance, and do you know the derivation?
No, sir.
Okay. So inductance and all that we have seen in circuits, like we draw them like this, but in reality they have to be made. Inductors are such things that you will not directly get in the market, except no, not except, you will not get. You have to design and make yourself, or maybe order. Like what I mean to say is like capacitor and resistor, they come in standard values in market. For inductor there is none. You have to make. So how do we make inductors? There are several types of course. We will not go into that kind of discussion. um, I will take a simple example here of a C core. Say it looks like this. There is some air gap present. So this thing is made of magnetic material, maybe iron, maybe ferrite, depending on at what frequency you are intending to operate. Now this has a winding in this fashion. Okay. Now this becomes an inductor. Now what decides the value of the inductance? The value of inductance is decided uh, ideally by the number of turns that you have here of this coil and the geometry of the magnetic circuit. Okay, that decides the inductance, how much inductance you will get from this coil. Now we just saw that MMF is flux times reluctance, and reluctance, okay, we can keep it like this. It's flux times reluctance. Reluctance is the reciprocal of permeance. Okay, 1 by p. Now flux linkage psi, see phi is flux and psi is flux linkage. Flux linkage is number of turns times flux. Sorry, n phi. And flux linkage is given by Li. So if I amount of current flows through an inductor L, the inductor coil is experiencing a flux linkage of psi, is Li. And also the MMF is Ni, number of turns times current. Okay. Now from here we can write that phi is Li by N. Now if we replace this phi in this equation, what we have is Li by N times 1 by P, which is equal to Ni. Now I gets cancelled out. What you are left with is inductance is N squared permeance, or you can say N squared by reluctance. Now reluctance of what? The reluctance that this coil sees. What does it depend on? It depends on the magnetic circuit. Say for example, this coil, if you excite this will create a flux like this. This is the flux path. So whatever reluctance the flux path experiences, say for example, if I can assume, or let us not assume, so if I draw uh, an equivalent electrical circuit of this magnetic circuit, it will be like this. So this very small resistance is the reluctance due to the iron, and the large resistance is the reluctance due to the air gap. So the equivalent resistance that you have in this circuit is a summation of this Rg. Right now, this reluctance, say, or any reluctance, what does it depend on? It depends on the length of the magnetic field. Sorry, length of the path which the flux is traversing, and this divided by mu, permeability, and area of cross section. So you can understand that this is actually a 3D thing. It's actually a three-dimensional element, or what we call is a core, like this. It has a certain cross-sectional area through which the flux flows. So you can see that the inductance is completely determined by the geometry of the magnetic circuit and by the current, sorry, by the number of turns that you have wound in the inductor. Now, since we have gone this far, let us do one last thing. From this equation, MMF equals phi times R we can actually, this comes from Ampere's circuital law. So if I draw this C core once again, have you studied Ampere's circuital law? Or maybe if I write the equation, you will be able to recall. So this is the thing. Now, if I draw a Amperian loop here along the core, Ampere's circuital law says that closed integral of H dot dl gives you the total current enclosed by the loop. Now, if you assume that the magnetic material is infinitely permeable, then the whole drop of magnetic field intensity happens, or H happens, in the air gap only. So H dot G, that becomes Ni. Okay. H dot G means this length. This is G. Now this MMF, as I wrote here, Ni is phi r. Ni I have written it is H dot G. So basically H, or magnetic field intensity, is nothing but MMF per unit length. Phi is flux, which is flux density B times area of the magnetic circuit, and reluctance is L by mu A. Since this reluctance is offered by the air gap, the G by mu A. So basically from here, what we have is B equals mu H, or mu R mu naught H. Now why I mm, derive this equation is that, you see, this inductance, flux linkage, all of these very much depend on the geometry, how you are making, how your magnetic circuit core looks like, how is the winding, how many turns are there. But B and H, how much H will cause how much B, this is intensity and this is density. That is a material property that does not depend on the circuit. It's a material property. So now if I draw BH curve for magnetic material, that looks like this. So you can see that the slope of this curve is given by mu r mu naught. Now mu naught is a universal constant. So the value of mu r here is very high. For say iron and all, it's 4,000 to 6,000, in that range. Whereas here the mu r is very low. The mu r is very low. Also, you see that the permeance is directly proportional to mu. You see here reluctance is inversely proportional to mu, so permeance is proportional to mu. So what happens is, when you keep on increasing the current, H increases. As a result, B increases linearly up to here. Beyond this, what happens is mu r drops, and as a result, the inductance drops. So basically, what I am trying to say from here is, inductance is not a constant. It's a nonlinear entity. Although I do not think in this course you have to you have to consider those things, but there is something called saturation, and whenever we are designing inductance, we make sure that it is always operating in the linear zone, because we don't want the inductance value to change during the circuit operation. If the current goes beyond its desired limit, the inductance value will drop. So just keep these ideas in your mind, that inductance is not a constant. Okay, so any doubt in this whole discussion? Why I'm spending so much time here is that after some time in this course also, to some extent, and in later courses, you have to study a lot of machine and power electronics, where magnetics is everything. So magnetic circuits are very important. Okay. All right. Now we'll start solving the problems. This one is kind of a formula based question. You read the question first. So two coils are in parallel with cumulative connection, which means this is one coil, this is another coil. They are magnetically coupled, and cumulative connection means both of them have the dots on the same side, right? Now if they have said that identical, so if this is L, this is also L, and their mutual inductance that depends on the coupling is M, say. Okay. Now the question is, and the current through the combination is reduced smoothly from 100 ampere to 0 ampere in 40 millisecond. So there was some current in the combination, means here 100 milliampere, sorry 100 ampere, and that would reduce. Now what happens is, if you have V or a pure voltage source across an inductor, then it's V equals L di dt, the equation becomes, and if you do V dt equals L di, it's a constant voltage. I should write, let us write as capital V. And if you integrate it for some time 0 to t, 0 to t, what you will get is V times t equals L times I. In other words, a pure inductive circuit, when connected or supplied from a DC voltage source, the current becomes linear. It rises linearly, or if it drops linearly. So that's what they have said. In 100 ampere, smoothly is not a scientific term, should have written linearly. 100 ampere to 0 in 40 milliseconds. So what we have is V by L, since it is linear, delta I by delta t. So what we can write is V, and the induced is 220 volts. So 220 by L is equal to delta I is 100 minus 0 in 40 millisecond. Now if you solve this for L, the value of L that you will get is 0.088 Henry. And for this equivalent circuit, this is a LEQ, okay? For such a combination, the equivalent inductance LEQ is given by L1 L2 minus M squared by L1 plus L2 minus 2M. Okay, now since in our case L1 and L2 are equal, say I write L1 equals L2 equals L, then I can write L squared minus M squared by 2L minus 2M, which becomes L1, sorry, L plus M by 2. L plus M by 2 is 0.088. So from here we can write one equation, L plus M equals 0.176 Henry. So one equation we have. Now the other equation you have to find out from the other condition, when the coils are connected differentially in series, the total flux linkage is given. So now the coils are connected differentially in series. So if one dot is here, another one is here. You can also draw it like this. Same thing. In this case, the equivalent inductance becomes L1 plus L2 minus 2m. In this case, it becomes 2 times L minus m. As the inductors are ideal, so you're writing L1 equals L2 equals L. Now the question says that total flux linkage is found to be this much Weber turns for a supply of 8 ampere. Now psi flux linkage is Li. So we can find out the Leq, which is psi by I, 0.016 by 8, 0.002. So 2 times L minus m becomes 0.002. So from here we can write L minus m is 0.001. So now we have two equations. One is this, another one is this. We can solve this very easy. So I'm just writing the final answers. L would become 0.0885 Henry and m would become 0.0875 Henry. Question is coupling coefficient is how much? So m is k times square root of L1, L2. In this case, they are equal, so k times L. So coupling coefficient becomes m by L. If you do m by L, definitely it will be very close to 0.9. Obviously, option D will be the answer. Okay, any doubt? All right. Next question. In the circuit shown in figure 2, it is found that the input voltage Vi and current I are in phase. Now the circuit is containing inductor, capacitor and resistor. Since the supply voltage and the current are in phase, so there must be resonance happening in the circuit. So the inductive reactance is magnitudinally equal with the capacitive reactance. This much we can say. If the coupling coefficients between the coils is denoted by K, find the value of K and the dot polarity of the coil PQ. Now they are in series. The inductors J20 and J12, they are in series. So we know that in such case, the equivalent inductance becomes L1 plus L2 plus minus 2M, depending on whether they are aiding or opposing each other's flux, plus minus 2M. Right? Now, how much is L1 and L2? They're J12 and J20. So J32 plus minus 2M. On the other hand, the I should not write. Okay, I should write X L. On the other hand, XC and not 2M, 2 omega M. On the other hand, XC is minus J4. So definitely we have to have a J4 here, then only we can have resonance in this circuit. So this sign has to be negative. This sign has to be negative. So we can say that J32 minus J28, that will give us J4. So we have to have a negative, means they are opposing each other. So if the dot is here in the question, the other dot must be here. then only we will get a minus sign. So definitely the dot will be at P, right? Now other question is find the
Sir,
value of K. Yeah,
hello.
yeah.
Sir, how to come to omega m?
I am writing the reactance. The inductive reactance is omega L, right? L is self-inductance, M is mutual inductance. So self-inductance, the reactance is omega L. For mutual, the reluctance is, the reactance is omega M. Basically, you multiply omega with this. So XL is omega times LEK. Okay.
But sir, omega not used L1 and L2. L1 plus
Sorry,
L2 in case J2.
I couldn't
Means,
get your question.
uh, sir, we do L1 plus L2,
Hmm.
J20 plus J32. So here omega not used in.
No. You see, look at this question. Here it is J20. J20, it is not 20 ohm. It is not written in some Henry. It's already in
Sorry, sir.
ohm. Already in ohm means they have already considered the frequency here.
My
But here
means,
I was,
L equivalent is equal to L1 plus L2 plus minus 2m, and you convert L into XL by saying
yes,
X
yes.
equal to omega LE, and L1 plus L2 when I do, then where it's omega.
Yes, the question, in the question we have been given omega, ohm, means they have already given us reactance. Right?
G20 L है या
You might,
XL है?
you tell me whether it is L or XL. It is J20 ohm. It's J20 ohm. Is it L or XL? What is the
XL,
unit of L?
XL, this is XL, not L, because L is Henry and
Yes.
there is ohm. XL is
So it must be
J20 as
XL. So they have given XL. So basically you multiply omega with this equation.
and lastly, how to come J4?
The question says that the input voltage and the current are in phase. Okay, and the circuit contains R, L, and C. Still, the voltage and current are in phase, so the circuit must be operating at resonance. So, if the circuit is operating at resonance, that means the capacitive reactance and the inductive reactance are equal in magnitude, right? Then only you can have R plus Jx minus Jx. Plus Jx is the inductive reactance, minus Jx is the capacitive reactance, which gives you R. Only R. Pure resistance, that is resonance is happening, right? Now capacitor they have given us J4 minus J4. So the mutual inductance between these two coils has to be such that the equivalent of the whole inductance of the whole coupled inductor is equal to J4 ohm. Then only it will exactly cancel the capacitive reactance and we will have a resonance in the circuit.
XL is equal to XC in case of resonance. So why we J30 plus 2 omega is equal to J4?
So it has to be J4. Now you see J32, it has to be J4. So the other member has to be minus J28. Since the other member has to be negative, we know that the dot has to be at P terminal. It has to be opposing or
Where
differentially
J20,
coupled.
so from where J28 comes?
I have J32. I want to make this J4. You tell me how much to put
Yes,
here.
yes, yeah, I understand. J28 minus we do.
And it is minus. So the minus sign tells us that the dot has to be at P. They are differentially coupled.
Okay, sir.
Right? Now, so now what we have here, then we have 2 omega m equals 28, or not 28. Yes, 228 omega mj. So what we have from here is omega m equals 14. Now you see this equation, m equals k root over L1 L2. If you multiply both sides by omega, then the right hand side you can also write as right. So we need not know the free operating frequency to find out the uh, coupling coefficient. Coupling coefficient we can directly say it is k equals m, whatever we got, 14 by square root of 20 times 12. 14 is the mutual inductance, the reactance of the mutual inductance that we got, and 20 and 12 are the individual inductances. So this will give us the value of k. Somewhere at 0.9. This will be the answer. Okay, any more doubt? Okay, we'll go to the next question then. All right. So first of all, this question, there is a technical mistake in the sense they have given 5 millihenry here and 2 millihenry here, whereas they have said that the mutual inductance is 4 millihenry. This cannot be true, because mutual inductance is given by case root L1 L2, there is k root 10. So the maximum value of mutual inductance can be root 10, which is 3 point something. It can never be 4, okay? But anyway, we can still solve the circuit. But this cannot be 4. It has to be less than 3 point something, square root of 10. Okay. So look at the question first. The voltage source is supplying a circuit, and the circuit is a magnetically coupled circuit. So there is a 50 ohm resistance first in series. Then it is supplying a 10 ohm resistor there, which is isolated, electrically isolated. So definitely the 10 ohm resistance is getting supply from the VS, from the voltage source VS, but through a magnetic isolation. So you can see this is a transformer. So if the VS is supplying a transformer, how much equivalent impedance does the voltage source see? Is the question clear? Okay. What we have to do is we have to carefully write the voltage equations. First, we will write in current domain, sorry, time domain, then we'll convert it to frequency domain. Same thing though, you can do in current time domain also. Okay. So let us first decouple the circuit the way we have done before. So if we decouple the circuit, it will look like this. So this is the voltage source, resistance, inductor. The decoupling will give us a dependent voltage source here. And the other side of the circuit, they are no more magnetically coupled. Like this. Okay. So this is R, this is L1, this is L2, this is R1 I am writing, say. We already know the values of L1, L2, I am just writing. Now, the question is how to write the polarity of these dependent voltage sources and their values. That would depend on the coupling. You see the dots are present here and here. So, oh, they have already given I1, I2 like this. Okay. So, I put I1 in this way, I2 in this way. And there is a dot here. So definitely if I2 is going to the dot, I1, this I1 is going to the dot of 5 millihenry, that will create a positive voltage on the dot of the 2 millihenry. So it will be like this. M di1 dt. And similarly, I2 is also going into the dot, so it will create positive voltage. So it will be you tell me whether it is clear up to this, that we can draw this circuit from the other circuit, whether you can understand the polarity of the dependent voltage sources. Okay, so now we will write equations. First we will write in time domain, then we'll convert to frequency domain. That will make solution easier. This is Vs. So if I write for the left hand side circuit first, what we have is Vs equals voltage drop I1 R1 plus L1 di1 dt plus another voltage drop M di2 dt. And for circuit 2, we can write, so here is polarity so that I don't make a mistake. Say start from here, minus I2 R2 voltage drop, again a voltage drop, minus M di1 dt, again a voltage drop, plus to minus L2 di2 dt equals 0, equation 2. I will make all these negative signs plus. Okay, now I will convert this into frequency domain. This is basically Laplace transformation. So in frequency domain, we know that inductance becomes j omega L, right? So we can write Vs equals, the first equation I'm writing, I1 R1 plus J omega L I1 plus J omega M I2. And the second one becomes I2 R2 plus J omega M I1 plus J omega, actually this was L1, L2, I2 equals 0, equals 4. Right now they are in frequency. Now what we have to do is, we have been asked to find out the equivalent impedance seen by the source. So basically we have to find out the equation between Vs and I1. So we have to eliminate I2. We have to eliminate I2. So what we can do is we can replace I2 from equation 4. We can find I2 from equation 4. So I2 in equation 4 would give you we have I2 here and here, so minus J omega M I1 by R2 plus J omega L2. Okay, this I put in equation 3. When I substitute I2 in equation 3, what we get is Vs equals I1 times R1 plus J omega L1 and is plus J omega M replacing I2 minus J omega M by R2 plus J omega L2 I1. So I1 again I can take common, I1 R1 plus J omega L1. Now here you see J times J is minus 1, minus 1 gets cancelled, so it becomes plus omega squared M squared by R2 plus J omega L2. So this is the equivalent impedance that the circuit sees, sorry, that the voltage source sees. Okay, now the next part is to simply put the value. All the values are given. If you put the value, as I said, that I can do it using the complex mode of my calculator, or you can do it manually also by complex algebra. If you put all the values, I did it with my calculator and I got this one, option C, 70 plus J5 ohm. Is it clear? Okay, let us take a 1-minute break, then we will carry on. Okay, we'll resume. So this question is clear. All right, we'll look into this question. So this is basically a transformer. Last one also was a transformer. Uh, Says nothing about the transformer, so we can say it's an ideal transformer with trans ratio 1:n. It shows a circuit where the source is connected to a load of 6 minus jx, so capacitive load, via a single phase transformer with trans ratio 1:n. The source impedance is 2 minus j6. Source impedance is also capacitive. That's unusual. Find out the values of n and x for maximum power transfer from source to load. Have you studied transformers yet? So what we can do is we can transfer this inductance, this impedance to this side. Since it is 1:n, so ZL referred to the primary side, ZL prime will become ZL by n squared. So it is 6 by n squared minus j x by n squared. Now maximum power transfer theorem says 2 minus j6 has to be equal to 6 by n squared minus j times x by n squared. Now we can equate the real and imaginary terms, which would give us 2 equals 6 by n squared, that is n is square root of 3, and 6 equals x by n squared, that is x by 3, which gives us x equals 18. Oh, very easy question. Okay, we'll go to the next question. Why is it there? Not working? Oh, all right. This question is tricky. It looks difficult, but it's actually very easy. Just look into it. For the coupled coils shown in figure this, so they have given some value of current, and the currents are not constant, they are dropping exponentially. I1 is this, I2 is this. What is the total energy stored in the system? Okay, now what this question tests or asks is whether the mutual inductance stores any energy or not. Like we know that if there is a current I flowing through an inductance L, then the energy stored in the inductor is half Li squared. But there is no energy storage associated with the mutual inductance. Okay, so basically what we have to do is we have to find out how much current is flowing through each inductor at t equals 0, and then find out the energy. So I1 0 is definitely 4 ampere. Just put t equals 0, t equals 0 is 1, and I2 0 is 5 ampere. So at t equals 0, 4 ampere current is flowing in this direction, 5 ampere is flowing in this direction, so total 9 ampere is flowing in the 10 Henry inductor. and 5 ampere through the 3.6 Henry inductor. So the total energy is half L I squared plus half L I square. Whatever you get, that much joule will be the answer. Any doubt? Okay. This one is a very interesting question. I don't know whether you have already studied transformer equivalent circuit. Now, basically, a transformer. Look at the question figure 2 first. It is a transformer, and figure 1, 6.1, is its equivalent circuit. But this transformer is expressed in kind of an unusual way. Generally, when we talk about transformer, we do not express transformers in terms of their self and mutual inductances. We express them in terms of their magnetizing reactance and the leakage reactance, or magnetizing inductance and leakage inductance. So how to relate between them? This question asks you to find the equivalence between these two circuits. Okay. So to start with, we have to quickly decouple the coupled circuit here in question 6.2. I will take a current I1 flowing in this direction and a current I2 flowing in this direction. So similarly, a current I1 is flowing here, I2 is flowing here. They're equivalent, right? Now, once I decouple them, the circuit becomes like this. I'm not going to explain how am I getting the polarity, because we have already explained it twice. If you do not understand, ask me. So this is L1, this is L2, I1, I2, A, B, C, D, here, here, here. It is coming this way, so M coming this way, so M. So from here we can write that VAB is equal to L1 di1 dt plus M di2 dt, or in frequency domain I can write VAB equals I1 times j omega L1 plus j omega M. Similarly, for the other part also we can write I2 times j omega L2 plus j omega M. Okay, this is what we get from this. Now say I am writing this for the time being as Lx, Ly and Lz. If I write this, then from the first circuit, so this is from the second circuit, from the first circuit we can write VAB equals, you can see, yeah. So Lz is carrying a current of I1 plus I2. Okay, I will write in I1 plus I2. So VAB equals I1 j omega Lx. I'm applying KVL in this loop, plus I1 plus I2 times j omega Ly. I can simplify this and write Mm. Sorry, here was a mistake. This is I1 and that one is I2. Cannot take common here. This I1 and this is I2. Yeah. So yeah. So what we are doing, I1 times j omega Lx plus j omega Ly plus I2 times j omega Ly. Sorry, not Ly, it's Lz. This loop. So by symmetry, I can write the equation on the other side, which would give me VAB equals I1 will become I2, Lx will become Ly. From here you can see Lx will become Ly, Lz will remain the same. Now if you compare the equations in set 2 and set 1, is I1 times something plus I2 times something. Here also is like this. So if you draw equivalence, you can write that L1 equals Lx plus Lz, and from here if you write, if you can see, L2 equals Ly plus Lz, and from here we can say that M is equal to Lz. Okay, so the question, say if you are given a transformer like this, instead of saying the leakage and all, you are told about the self inductance of the primary and secondary coils and the mutual inductance. From there, in this way, you can find out their Lx, Ly, and Lz. So Lx is the leakage inductance of the primary, Ly is leakage inductance of the secondary, and Lz is the mutual inductance. Sorry, not mutual, the magnetizing inductance. You can say, you can verify this like this way. Say in question number, in figure 6.2, say in the secondary side there is no load connected, it's open circuited. So in that case, if you say supply some voltage here, all you will get to see is that there is a pure inductive circuit which is L1, whose inductance is L1. Similarly, if you do that here also, you will get an inductive circuit whose inductance is Lx plus Lz, and we can see from here that Lx plus Lz is L1. Okay, so now we can find out, we have been asked to find out L1, so L1 is Lx plus Lz, which is 45 millihenry in this case. I will write a bit far away, I don't want to ruin this. 45 millihenry. L2 is Ly plus Lz, which is 115 millihenry, and M is same as Lz is same as M, which is 15 millihenry. So this one is correct. Any doubt? Okay, go to the next question. These are a bit, okay, three-phase power. We'll do it later. Let us complete the magnetic circuit questions first. Then we'll do the three-phase power if there is time. A three-winding transformer is connected to an AC voltage source as shown in this. The number of turns are as follows: N1, N2, N3 they have given, and the magnetizing current is neglected. The currents in I2 and I3 are given. What is the value of the current I1 in ampere? So definitely current will get reflected. It's in the inverse proportion of turns ratio. I1 N1 equal to I2 N2 is equal to I3 N3. Actually, in a more general way, it is I J Nj equals 0 for a transformer. This is called MMF balance of a transformer. Okay. So the best way of solving these circuits, this kind of circuit, is to draw a transformer by yourself, then look at the dot that have been given in the question and draw the windings in that fashion. Obviously not during exam, but for your understanding, the way the dots are given, you draw the circuit in that fashion, put the dots, and then find out in what direction. So this question actually not only asks you about the current transformation, it also asks, see whether they're vectors, right? So the direction matters. Basically, this is the question. Find out the plus and minus. Okay. Now, by the definition of dot convention, we know that if you have things like this, an increasing current here, I, will give rise to a current here, I2. If di dt is positive, di1 dt is positive, then I2 is also positive. So in time domain, this becomes so in frequency domain, it becomes I1 equals I2 plus I3. You see here, I1 is entering the dot. Both I2 and I3 are leaving dot. So this will become, oh, I leave I2 plus I3. And they have to be reflected to the primary side, refer to the primary side. Now, the rest part is easy. So refer to the primary side, it will be N2 by N1 for the I2. So 100 by, let me write like this, N2 by N1 I2 plus N3 by N1 I3, which gives you 1 by 5 times 2 angle 10 plus 2 by 5 times 2 angle 170. So you can find this out with a complex calculator. I did it once, none of the answer matches. So I will just tell you the answer. The answer comes out to be 0.45 angle 152 degree. Okay. Any doubt? We'll look at the next question then. This one is an interesting question. We were discussing about inductor. Now this is a question about inductor. The magnetic circuit shown in question 11 has dimensions AC equals AG equals 16 centimeters squared. So AC, AG, you can understand their area. Magnetic core area AC, air gap area AG. So this area, if I draw this, then this area. This area is AC. Similarly, that for the air gap is AG. That is 16 centimeters squared. And gap length is 0.05 centimeters, is half millimeter. Length of flux path through the core is 30 centimeter. So flux path through the core is 30 centimeters. So this length is 30 centimeter. And number of turn in the coil is 225. Relative permeability of the core material is 70,000. This is quite large. And for the condition that the magnetic circuit is operating with flux density 0.9 Tesla, find the current I. So how much current should be pushed in this circuit such that a magnetic flux density of 0.9 Tesla appears in the magnetic circuit? So we have been given the magnetic flux density B. Now B is flux by area, flux density, flux per unit area. Okay. Okay, we have to find out what? We have to find out the current. So let us start with current. Let us see if we can directly it from here. Now psi is Li. So basically with the data that we have been provided with here, we can find out the inductance of this coil. Let us see how much we can simplify the task. So I is psi by L. Inductance we can find out. Now psi is N phi by L. Phi is B times A. B times A, and L is N squared psi B times A, and there is one N is N squared permeance, the total permeance that the coil sees. So it becomes B A by N P. Now BA by NP, I can write BA by N times the reluctance, the equivalent reluctance of the circuit. Okay. Equivalent reluctance of the circuit. Now, what will be the equivalent electrical circuit of this magnetic circuit? We discussed this. It will be like this. So the equivalent reluctance will be a summation of the reluctance of the magnetic core. Say I call this Ri, R iron, and R gap. So Ri plus Rg will give you R. So what we can write from here, so we started from I, so I equals Ba by N R. R is, say, length of iron by mu R mu naught so L by A, area of iron, plus reluctance of the air gap, which is length of the gap divided by mu naught. For the air gap, mu r is 1, relative permeability, times A. So this is basically the A that we are talking about here, this A, area of cross section. So that gets cancelled out. What we are left with, we can take mu naught also outside. What we are left with is Li by mu r plus Lg. Now we have all the data. So you see they gave us the area value, but we do not need the area value, it looks like. Let me see if I, okay, so now we have all the data, right? 25 times mu naught is 4 pi into 10 to the power minus 7 times Li. Li is 30 centimeter. 30 10 to the power minus 2 by mu r is 7 10 to the power 4 plus Lg is 0.05 10 to the power minus 2. So some value I got, which is 1.605 ampere. They have asked in milliamperes, so 1605 milliampere. So this is the answer. You can do it in a more this is a straightforward way also, but you can, if you are curious, you can say from here you can find out the reluctance, then you can find out the permeance, then from here you can find out the inductance, n squared permeance, so you will get some millihenry. So in this way we calculate inductance. Okay, you get a feel that if I buy this a core which has this dimension and this value of mu r, and if I wind 225 turns in the core, what we will get is this much millihenry inductance. Okay. Okay, any doubt here? Deepak, are you there?
Yes, sir.
Okay. Okay, then we'll go to the next question. Same kind of question. There also here another inductor. It's the code looks different, nothing else. The iron ring of mean length 60 centimeter has an air gap of 2 millimeter, winding of 100 turns. The iron has a permeability of this much. They have given the permeability, not the relative permeability. The permeability they have given. And coil carry 1 ampere of current. What is the flux density? So it's the other way around. Whatever we had in the last. So we have been asked to find out P. B is flux density, which is flux per unit area. Now, flux is flux linkage by N, psi by Na, and psi is Li by N. Na was there. Now, from here we can write L as N squared permeance I by Na, which gives us Npi by A. I will write it in terms of reluctance, so it's easier to find out Ni by AR. Okay, now we will write the reluctance. So as you can see here also, the reluctance means two reluctances in series. So this becomes equal to Ni by A times 1 by reluctance. So 1 by summation of the reluctances. So length of the iron, reluctance due to iron, length of the iron by mu of iron times area plus length of air gap by mu of free space, which is also mu naught actually, times area. So this area gets cancelled out. What we get is Ni by Li by mu I plus Lg by mu naught. So now if you put the values, B becomes N is 100, I is 1, Li is 60 centimeter. So I have to write in SI by 1.25 10 to the power minus 4. They did not give any unit. Maybe it's SI, looks like that. The 10 to the power minus 4 gives me an hint that it's in SI. That order. Plus Lg, it's 2 millimeter. So 2 millimeter, 2 into 10 to the power minus 3 by this should give you the value in Tesla. So 100 by 60 10 to the power minus 2. So in millitesla, it's coming as 15.65. So this is the answer. Any doubt in magnetic circuit in general? I hope you got an idea that how we make inductors, right? It's actually the other way around. You will be asked that you make an inductor of this much millihenry. You have to select the core and find out how many turns you need. There are other concerns also. You will be also told about how much current will be flowing through the inductor. So that will tell you how thick wires you need. Then you have to calculate whether that many wires, say 100 or 200 turns. 1 minute, in the question they say 100. Here it is 200. Maybe they changed from the last year's question. Anyway, so say 200 turns you have to wind of say something, say 5 millimeters squared cross section. Now whether that many or that much copper can be accommodated in this window space or not. If yes, good. If not, you have to take a larger core. Again, do the calculation. This is how we make inductors. Okay. Now what we were left with? 2 wattmeter method. Okay. So actually in general, if you have a n phase load, n phase balanced load, then you will need n minus 1 wattmeters to measure the power. Okay. So question is 2 wattmeters which are connected. Deepak, have you worked with wattmeter? Have you done experiments with wattmeter in your lab?
Yes, sir.
What are the two coils of an wattmeter?
Fixed coil and moving coil.
No, they are types of ammeters and voltmeters. A wattmeter has two coils in it. Yeah, what did you say? Fixed coil and moving coil. I think you are correct. Are they? No, they are not called like that. You heard about CC and PC?
Current coil, pressure coil.
Yes. So, in do you know how the connection is made in a 2 wattmeter method?
I not thinking that. Sir, ध्यान नहीं आ रहा.
Okay, we will do. So, say we will do this problem assuming a star connected load. Star connected load like this. Okay. Now it is being fed by a three-phase supply A, B, C. Now the load has a power factor of something, say 5, lagging power factor 5, let us say. That means all of them have individually lagging power factor 5. Okay. Now we will connect the wattmeters to measure the power. 2 wattmeters are there. So these two are the current coils of 2 wattmeter. 2 wattmeters. So one current coil say goes to phase A. Other current coil comes in parallel to phase C. Sorry, phase B. You can always do the change. It doesn't matter. You have to just maintain the phase sequence. And C has no current coil in it. And now we connect the pressure coils. Pressure coils are connected like this. So this pressure coil, both the pressure coils go to phase C. So this is the connection for 2 wattmeter method. So this is 1 wattmeter. We call this say W1. This is another wattmeter. We call this W2. Okay. Now you can see that this point is A, B, C. This is N. Okay, neutral. All right. Now this wattmeter W1, let us say it reads minus 21 kilowatts. So it may also happen that the total power is from your left side to right side, but one wattmeter is reading minus 21 kilowatt. It depends on the power factor. And the other one is reading 81. So definitely the total power that is being delivered to the system is 81 minus 21, 60 kilowatt. So the question is, how much is the apparent power? How much is the power factor? So to do that, we will quickly write down the voltage and currents. I am writing, you tell me if there is any doubt. So these are the phase voltages, and we take the load say as a lagging load of power factor 5. Then the currents will be right. And we will also quickly write down the line voltages, which will lead the phase voltage and will be 3 times the phase voltage. So any doubt in these equations?
How to come 150 degree?
You look here, it's 0 minus 120 plus 120. So if it is 30, this should be 30 minus 120. This should be 30 plus 120.
Okay, sir.
Okay. Now we will find out what is wattmeter 1 seeing. Now if you look at it from wattmeter 1's point of view, it sees the current IA, which is I angle minus phi. And what voltage does it see? The voltage that it sees is VAC. VAC, which is minus VCA. We have VCA here. So the voltage that it sees is root 3V angle 150 minus 180. Minus means 180 degree phase shifted. So root 3V angle minus 30 degree. So the power, instantaneous power, no, not instantaneous power, the active power. So the wattmeter is seeing this much current, I angle minus phi, and this much voltage. So the active power that it measures, P1, is simply Vrms Irms cos phi, cos of phi. So phi is the angular difference between the current and the voltage. So what is the angular difference? This is minus phi, this is minus 30. So the angular difference is, you can say, minus phi minus minus 30, that is minus phi plus 30. Since it is cos theta equals cos minus theta, I will write as cos theta phi minus 30 degree. Any doubt? Okay. Similarly, wattmeter 2, what does it see? It sees IB and VBC. It sees IB, which is I angle minus phi minus 120, and it sees VBC, which is root 3V minus 90. So how much of a difference, phase difference, does it see between the voltage and the current? It sees minus phi minus 30, which is this. Since cos theta is cos minus theta, I can take phi plus 30. So the power that it measures is, active power that it measures is root 3 Vi cos phi plus 30 degree. Now in the question they have given that the first one is, you can take anyone as the first, doesn't matter. First one is minus 21, second one is second is 81. So minus 21 kilo, 81 kilo. Now equation 1 and equation 2, we have to find out S and phi. So from now we can find out phi from whatever we have now. What we can do is, you divide equation 1 by equation 2. If you do that, that will give you cos phi minus 30 by cos phi plus 30 equals minus 21 by 81. Now cos phi minus 30, we can write cos 30 plus sin phi sin 30 by the same thing with a minus sign. So what is the next step, Deepak? It's addendo dividendo. That will give you cos phi cos 30 by sin phi, sorry, sin 30. We will take this minus on the numerator. That will give us 21 plus 81 that is 60 by minus 102. Did I do it correctly? I hope yes. Then if I add them, it becomes cos on the top and subtract. Yeah. So sin by cos. So what I can write is tan phi tan 30 is minus 102 by 60. From here you can find out phi, right? So we have been asked to find out cos phi. So cos phi is cos of tan inverse right? This will give you somewhere close to 0.3. This one will be the answer. You can verify. Now, once you know cos phi, let us also find phi. So phi will be cos inverse 0.3216 whatever. We're already done. It's already 8 p.m. Phi will be 71 degree. I will quickly finish. 71 degree. Now, from equation 1, we have something. Now, we have been asked to find out apparent power. Now, so in three-phase system, the power is √3 V line I line cos phi. So definitely the apparent power is √3 V line I line. Now see, in our case, what we have done, our I line, these, we already have a √3. We took them like this, it doesn't matter. So if I substitute, it will become 3 VI. Basically, this V is phase voltage. So V into I is the reactive power, sorry, apparent power is every phase because star connected system. So line current is phase current. So phase current times phase voltage gives you phase apparent power times three phases. So that's it, 3 times VI. Now, from equation 1 or equation 2, whatever you might want, you can take. See, if I take equation 2, it's in front of my eyes. So equation 2 says √3 V I cos phi plus 30. Phi plus 30 is 101 degree equals this. So from here we have to find out 3 VI. So you can easily find out. So root 3 VI becomes 81 by cos 1 not 1. That becomes root 3 VI, and I multiply another root 3 with it. That gives me some 735. Oh no, it's 186. Did I make a mistake? Ah, 60 by the power factor 0.3216 is 186. From here, the total power is 60, and we found out the power factor to be this. That gives you definitely 186. But where is the mistake here? Okay, let me do with the other one. Let us see if the same thing comes. 21 by cos 71 minus 30, so 41 times root 3 is giving 48. No, something is wrong. Let me check if this equation is correct. Cos of tan inverse minus 102 by 60 times 1 by tan 30. Oh, okay, phi is minus 71. Okay, I shouldn't have done this. See, there is a minus sign here. My mistake. So this is cos of minus 71 degree. Since cos theta is cos minus theta, this somehow avoided our attention. This is 0.321, so that doesn't change, but phi is minus 71. So minus 71 plus 30, which is minus 41. Now let us see if it matches. 81 by cos 41 and times root 3. Yes, 185.8. 86, whatever. So this is apparent power. What is the unit, Deepak?
KVA.
kV.
A.
kVA. And suppose if I write reactive power, then what is the unit?
KVAR.
Yes. So do not make a mistake there ever. Okay, any doubt here, or else we will stop for today.
Sir, one request, please upload lecture today or tomorrow, so we revise this lecture in proper time duration. We can remind it.
Okay, I will upload it right now. Within 2 hours, you will get it in YouTube.
Thank you, sir.
The next question is easy actually. It is the other way around. They have given you the power factor. I will just give you the hint how to solve. The power factor they have given, total power they have given, how much are the watt meters reading they have asked. So we have been asked to find out P1 and P2. Okay. So they have given you P1 plus P2 equals 20 kilowatt or kilowatt, 20. And we know that P1 is say root 3 vi cos phi minus 30. And P2 is root 3 vi cos phi plus 30. Phi they have given, right? Phi they have given. So you can find this out as wait, how did I solve? Yeah, so from here what you can do is if you do P1 by P2, you will get cos phi minus 30 by cos phi plus 30 by addendum dividendum, or what is that called? What you will get is P1 plus P2 by P1 minus P2 equals cos phi cos 30 by sin phi sin 30. You see the right hand side, you know phi value is given, and P1 plus P2 also you know. So from here you can find out P1 minus P2, some value you will get. So now you have P1 plus P2 value, you have P1 minus P2 value. You can solve this and get P1 and P2. Answer will be this one. Just do it this way, we'll get the answer. Okay, we'll stop for today here. We'll meet next Monday. Next Monday will be the class 6 to 8, and so today is 2nd October. Okay, today is 2nd October. Our next scheduled class is 9th October, and next to next is 16th October. 16th October class I am not taking, and I have preponed that class to 10th October. So next week there will be 2 consecutive classes. One on 9th October Monday, other one will be 10th October. 9th October Monday is the usual slot 6 to 8. The next day Tuesday 10th October again 6 to 8 p.m. will be the next and last class of this course. Thank you.